Current AI agents suffer from extreme cognitive redundancy, treating simple edits like massive codebase audits. When you ask a human engineer to change a single icon on a website, they do not read the entire codebase first. They locate the file, make the change, and verify it. However, state-of-the-art AI agents often default to a maximum context-first strategy. They reread files, rebrowse directories, and reanalyze architectures for even the simplest tasks. This video explores a groundbreaking paper that addresses this inefficiency by teaching AI agents to recognize when a task is simple, saving up to 85% in execution costs. We can mathematically measure an agent's wasted effort using the Agent Cognitive Redundancy Ratio. To solve this problem, the researchers first formalized the concept of minimum sufficient execution. This is the absolute lowest cost path that still guarantees a successful task completion. By comparing an agent's actual execution cost to this ideal minimum, they define the Agent Cognitive Redundancy Ratio, or ACRR. A high ACRR indicates massive wasted effort. Interestingly, the researchers discovered that this cognitive redundancy is actually at its worst on the simplest tasks, where agents overprepare the most. The E3 framework replaces exhaustive search with a three-stage process: estimate, execute, and expand. Instead of gathering all possible context up front, E3 forces the agent to act like a human engineer. First, it estimates the task's difficulty and scope. Second, it executes a minimum viable plan tailored to that estimate. Third, it expands its scope only if verification fails. This shift from maximum context first to progressive expansion keeps the agent lean while preserving its ability to solve complex tasks. Upfront estimation allows the agent to establish a cheap, optimistic starting point for execution. The agent uses cheap lexical cues and quick structural probes to predict an initial operating point. This includes estimated difficulty, scope, risk, and confidence. Crucially, this estimate is designed to be cheap and optimistic rather than exhaustive. Based on this estimate, the agent executes the smallest possible path. For a simple task, it edits a single localized site and verifies it immediately, completely bypassing the need to read irrelevant files or run heavy repository-level tests. Verified progressive expansion acts as a safety net, allowing the agent to recover safely from underestimation. If the agent's edit fails verification, E3 does not restart from scratch or panic read the entire repository. Instead, it progressively increases the scope level by 1, reusing everything it has already learned. It traces dependencies and follows imports to find hidden couplings. This progressive context expansion ensures that the agent only pays for deeper reasoning when there is concrete evidence that the task requires it. E3's design is inspired by classic power system engineering solvers that use warm starts and iterative refinement. In power flow analysis, solvers do not search the entire state space. Instead, they compute a cheap, structured initial guess, called a flat start or warm start, and refine it iteratively using Newton-Raphson steps. E3 applies this exact discipline to AI agents. The upfront estimate acts as the warm start, landing the agent in a workable region. The execution and expansion steps act as the iterative refinement, ensuring fast and stable convergence without unstructured searching. On a controlled benchmark, E3 matches the success of the strongest baselines while cutting costs by 85%. To evaluate E3, the authors built MSE-Bench, a deterministic benchmark of 121 code edits. The results are striking. E3 achieved a 100% success rate, matching the most thorough baseline. However, it cut overall costs by 85%, reduced tokens by 91%, and inspected 92% fewer files. While other cheap baselines failed on complex tasks, E3 remained both highly reliable and incredibly lean, proving that upfront scope judgment is the key to efficient agent execution. Real-world testing with GPT-4o confirms that E3 is the fastest and most token-efficient policy on live codebases. To ensure these findings hold up in the real world, the researchers created LLM Case, a harness testing a live GPT-4o agent on a real open-source library. The results confirmed that aggressive overreading carries a massive operational tax in terms of latency and API limits. E3 emerged as the leanest and fastest policy overall. It spent 18% fewer real tokens and had 18% lower latency than the thorough agent, demonstrating that E3's benefits translate directly to real-world developer tools. While highly effective, E3's current limitations point toward exciting future research in learned estimators and complex dependencies. Currently, it relies on a simple lexical estimator, though a learned or LLM-backed estimator could generalize much better. Additionally, the benchmark focuses on import-based dependencies, leaving other hidden complexities like dynamic dispatch or runtime reflection for future work. Ultimately, this research is a major step toward engineering-grounded AI, encouraging us to build agents that match their cognitive effort to the actual engineering reality of the task.